As the Earth spins effortlessly through space, gravitational forces drive its motion. Here is the Earth's electromagnetic field. Where does it originate from? How do we produce an electromagnetic field in the Earth? Well, the geodynamo is the process where the movement of molten iron in the Earth's core generates the planet's magnetic field. The Earth is comprised of 4 parts, with the outer core containing molten iron and nickel. As the Earth rotates, the movement of these molten metals generates electric currents, the geodynamo process, producing the magnetic field. So magnets are created from metals like iron or nickel, as they are magnetic materials found in the Earth's outer core. Magnetic materials have a magnetic field around them. This is what attracts other magnetic materials towards them. The magnetic field lines of a bar magnet show concentric circles around the edges pointing towards the South Pole, and field lines coming into the South Pole and out of the North Pole on the ends of the magnet. Current-carrying wires also have a magnetic field. Here we have the flow of electrons from the negative to the positive terminal. This is because electrons are attracted to the positive terminal as they are negatively charged. The definition of conventional current is in the opposite direction, from the positive to negative terminal. You will be told in your exams the direction of electron flow or conventional current. Here current is flowing in a wire towards the right. We can use the right-hand rule to determine the direction of the magnetic field, which is always in the form of a loop for current-carrying wires. Here current is flowing up the wire. Your thumb shows the direction of the current, in this case upwards. The direction of your fingers show the direction of the magnetic field. Due to the current flowing upwards, the magnetic field lines point anti-clockwise. This is shown by the right-hand rule. Try it out with your right hand. Let's have a look at what happens when you combine 2 magnetic fields, one from a current-carrying wire, and the other from the North to South Pole. When a current-carrying wire is placed in a magnetic field, it experiences a force. That's why we observe the wire with current rotating. 2 magnetic fields are interacting, causing a force. The force is the greatest when the current-carrying wire is 90 degrees to the magnetic field. The force becomes 0 when the wire is parallel to the magnetic field. This phenomenon is called the motor effect. We can define the motor effect as the force experienced by a current-carrying wire when placed in an external magnetic field. This force is the result of the interaction between the magnetic field around the wire and the magnetic field it is placed in. Fleming's left-hand rule helps us to determine the direction of the force once we know where the North and South Pole is, and the direction of the current. Using your fingers, your thumb represents the direction of the force, your index finger the direction of the magnetic field, which is always pointing towards the South Pole, and your second finger presents the direction of the current. Now let's apply all the concepts we have learnt to exam practice questions. Figure 7 shows a wire passing through a piece of card. The wire carries an electric current. Draw one magnetic field line on Figure 7 to show the shape of the magnetic field produced by the current. We know from observing the magnetic field lines of a current-carrying wire, the magnetic field lines take the form of loops. So we need to draw one loop around the wire. The question then asks, draw one arrow on the field line you have drawn to show the direction of the magnetic field. Let's use our right-hand rule to help us work this out. From Figure 7 it shows us that the current is flowing downwards. That means our right thumb must point downwards. Which direction are your fingers curling towards? You should have found they curl clockwise, so let's draw this onto our diagram. The 2 lines we drew gain you 2 marks. One mark is for the loop, and the second mark is for the arrow pointing clockwise. A metal rod XY is placed in a magnetic field as shown. Wires from a cell are connected to the ends of the rod so that there is a current from X to Y. Describe the effect on the rod. The question tells us a metal rod is placed in a magnetic field, so we have one external magnetic field. The question also tells us that rod XY is connected to a cell so current flows through it. What happens when current flows through a wire? A magnetic field is produced, so we have 2 magnetic fields interacting. one from the wire and the other from the external field. Therefore, we have two magnetic fields interacting. This would result in a force acting on the system due to the motor effect. We can see from the diagram that the wire is perpendicular to the magnetic field. From the motor effect, we know the force is the greatest in this position. This question is worth 2 marks, so we need to write 2 points to describe the effect on the rod. The first thing we need to state is that there will be a force acting on the system, as there are two magnetic fields interacting, one from the external magnetic field and the other from the current-carrying wire. We can determine the direction of the force using Fleming's left-hand rule. Pointing your index finger upwards, as shown in the diagram for the magnetic field, and second finger to the right, from X to Y, we find that the force is acting out of the page. Here is our completed answer for 2 marks. Diagram 1 shows some of the apparatus used to investigate the force on a current-carrying wire XY in a magnetic field. Diagram 2 shows the poles of the magnet viewed from above. Draw the uniform magnetic field between the poles. Firstly, what is a uniform magnetic field? Well, a uniform magnetic field can be described as being constant at all points, so pointing in the same direction in all areas, and of constant strength throughout the area it occupies. How is that represented scientifically? Well, a non-uniform magnetic field would look like this, with the arrows pointing in different directions and an uneven spacing between them the further you go outwards. A uniform magnetic field would look like the opposite of this. A uniform magnetic field has an even spacing between each arrow, they are parallel and point in the same direction at each point of the area they occupy. So we need to draw this between the north and south pole in our diagram. Remember, our field lines must always point in the direction of the south pole. You will gain 2 marks in this question if you space your field lines evenly and point them towards the south pole. The current carrying wire XY is at right angles to the magnetic field. The current in the wire is 10 amps. Suggest why the wire used in this investigation must be thick. Well, from being told 10 amps of current is being passed through the wire, that is quite a large amount of current. When large currents are passed through wires, the wires heat up. In order to reduce this heating effect, we can increase the surface area of the wire by making it thicker. This prevents the wire from heating too much and melting. Explain why the wire XY experiences a force when there is a current in the circuit. We know that the wire XY is at right angles to the magnetic field, and current is flowing through the wire. That means we have 2 magnetic fields interacting, as current-carrying wire also has a magnetic field. Since they are at right angles, the force will be the greatest, and we can use Fleming's left-hand rule to determine the direction of the force from the direction of the magnetic field and current. State 2 ways in which this force can be reduced. This force was created from the current-carrying wire and the external magnetic field interacting. So to make the force smaller, we would need to decrease the current or decrease the strength of the magnetic field. Thank you for watching the video, and please leave any questions you have in the comment section. Don't forget to subscribe and see you in the next one.